Hello everybody. For today, we're going to have some special types of discrete random variables. The first of which would be discrete uniform distribution. A random variable x has a discrete uniform distribution if each of n possible values in its range x sub 1, x sub 2, up to x sub n has equal probability. Then f of x is equal to 1 over n. The mean and variance of the discrete uniform distribution would be a plus b over 2 for the mean. So the mean is the expected value, so it would be a plus b over 2. While for the variance, it would be b minus a plus 1 quantity squared minus 1 all over 12. Let's have an example. If the range of x is in the set 0, 1, 2, 3, 4, with the probability of x equal to x is 0.2, determine the mean and variance of the random variable. Consider that this is a uniform distribution with the uniform probability 0.2. So we are given with f of x is equal to 0.2, which is 1 over 5, consistent with the 5 values of x, 0, 1, 2, 3, and 4. The probability of x is equal to x is 0.2. The mean is equal to a plus b over 2. So that is 0 plus 4 over 2 equal to 2. You can check this using the listing of all the probabilities and computing for the expected value of x, which is just the same, while the variance is equal to b minus a plus 1 squared minus 1 over 12. So that is 4 plus 1, 4 minus 0 plus 1 is 4 plus 1 squared minus 1 all over 12. So this is 25 minus 1, so 24 over 12. So sigma squared is 2. Next, let the random variable x has a discrete uniform distribution on the integers from 1 to 8. Determine the mean and variance of x. So for this, the possible values of x would be 1, 2, 3, 4, 5, 6, 7, and 8. So the mean is 8 plus 1 over 2. So that's 4.5. While the variance is 8 minus 1 plus 1 squared minus 1 all over 12. So sigma squared, or the variance, is equal to 64 minus 1 is 63 over 12. So this would be equal to, we can have it 21 over 4. Okay. Another example. Assume the wavelengths of photosynthetically active radiations are uniformly distributed at integer nanometers in the red spectrum.
that is from 657 to 700 nanometers. So you have A is 657 with B is equal to 700 nanometers. Letter A. What is the mean invariance of the wavelengths of the distribution for this radiation? So the mean would be 657 plus 700 over 2. So you can use your calculator for this. It would be 657 plus 700 over 2, which is 678.5. While for the variance, it would be 700 minus 657 plus 1 squared minus 1 all over 12. So, and using your calculator, that would be 161.25. For letter B, if the wavelengths are uniformly distributed at integer nanometers from 57 to 100, how does the mean and wavelengths how does the mean and variance of the wavelengths of the distribution compare to the previous part? So this time A is 57 while B is 100. So mean is 57 plus 100 over 2. So that would be 78.5. While the variance is 100 minus 57 plus 1 squared minus 1 all over 12. So that is 161.25. So observe that it follows the rule of expectations such that the expected value of x plus a is equal to the expected value of x plus a, since the expected value of a is a. So since all x's are increased by 600, so or since all of the values are decreased by 600, so the mean would also be decreased by 600. While for the rule of variances, the variance of ax is equal to a squared variance of x, and the variance of ax, the variance of x plus a is equal to the variance of x. So the variance would not change. Our second type of distribution is the binomial distribution. Binomial distribution has a Bernoulli trial, and the Bernoulli trial has only two possible outcomes. used so frequently as building block of a random experiment. The terms usually used are success and failure, which are usually just labels. We can just as well use A or B, or 0 or 1. Unfortunately, the usual labels can sometimes be misleading. For example, if we are looking for the number of defective components, the random variable x counts the defective parts. The production of defective part is also called a success. In a binomial distribution, a random experiment consists of n Bernoulli trials such that the trials are independent. So first trial is not affected by the second trial, is not affected by the third trial. Next, each trial results in only two possible outcomes, which we would be labeling as success and failure. Next, the probability of success in each trial, denoted as P, remains constant. Consider the following random experiment and random variables. Flipping a coin 10 times, let X the number of heads obtained. A worn machine tool produces 1% defective items, or defective parts. Let X the number of defective parts in the next 25 parts produced. Each sample of air has 10% chance of containing a particular rare molecule. Let X the number of air samples that contain the rare molecule in the next 19 samples analyzed. Of all bits transmitted through a digital transmission channel, 10% are received in error. Let X the number of bits in error in the next 5 bits transmitted. A multiple choice test contains 10 questions, each with 4 choices, and you guess at each question. Let X the number of questions answered correctly. 6. In the next 20 births at a hospital, let X the number of female births. 7. Of all patients suffering a particular illness, 35% experience improvement from a particular medication. In the next 100 patients administered the medication, let X the number of patients who experience improvement. The random variable X that equals the number of trials that results in a success has a binomial variable with the parameters P equal to 0 to 1 inclusive and N equal to 1, 2. The probability mass function of X is given by f of X equal to N combination X times P raised to X times 1 minus P raised to N minus X, where X is from 0 to N. The mean and the variance. If X is a binomial random variable with the parameters P and N, the mean is NP, while the variance is NP times 1 minus P. Sketch the probability mass function of a binomial distribution with N is equal to 10 and P is equal to 0.1, and comment on the shape of the distribution. What value of X is most likely and what value of X is least likely. Determine the cumulative distribution function of a binomial random variable with N is equal to 3 and P is 1/4. We can try to solve these problems using MATLAB. To solve this problem, first, we're going to define our symbolic variables. So sims, the random variable X, and f of X. And then after that, we list down all the possible values of X. So it would be from 0 to 10. So that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, for the command, we're going to use the binomial probability density function. So help Bino PDF. So the binomial probability density function. So it would be needing x, n, and p. To get f of x, to get the probability mass function, it would be equal to Bino PDF of x, the different values of x. Your n is 10 and your probability is p equal to 0.1. So let's not display the answers yet. So let's have semicolon. And then I want to display the answers in long so that we would be having more decimal places. So we can have the list down of all the elements PMF is equal to, for the x values, x, and then for PMF, so PMF. So we have the x, the first, this one would be the x values, and this is the probability mass function. So most likely is this one, when x is 1, and least likely would be when x is 10. So for this one, we have most likely, the highest one is when x is equal to 1, and least likely when x is equal to 10, the lowest probability. We can have its bar graph. So bar graph of PMF observe that the highest probability belongs to the second one. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So when x is 1, it is the highest, and we can't differentiate the higher values. Now for the second part, determine the cumulative distribution function of a binomial random variable with n is equal to 3 and p is equal to 1/4. So let's clear the variable first and then set PMF to be equal to x is from 0 to 3, and then we're going to evaluate the probability mass function using the binomial PDF, such that we have x and then n is 3, the probability is 1/4. So this is still the probability mass function. So we can have the list down of element PMF prime. So that would be this one. So for capital F, F1, the first one is the first value of PMF. The second one, F of 2, would be equal to F of 1 plus PMF for the second one. The next one, F of 3, is equal to F of 2 plus PMF of 3. And lastly, F of 4 is equal to F of 3 plus PMF of 4. So we can have the list down of element F prime. So we would be having capital F of X is equal to 0.4219. So we start with 0 when x is less than 0, 4219 when x is greater than or equal to 0 but less than 1, 0.8438 when x is greater than or equal to 1 but less than 2, and it is equal to 0.9844 when x is greater than or equal to 2 but less than 3, and it is 1 when x is greater than or equal to 3. So that's it. Next example. The random variable x has a binomial distribution with n is equal to 20 and p is equal to 0.5. Determine the following probabilities. So for this, we are going to write this down as 20 combination x, such that we have p is 0.5 raised to x, and then 1 minus p, so that's 1 minus 0.5, will be equal to 20 minus x. So basically this is just 20 combination x times 0.5 raised to 20. Determine the following probabilities. So let's have this one as the binomial of x. So letter A, for letter A, the binomial of 5. So that's 20 combination 5, 0.5 raised to 20. Use your calculator. So this is 969 over 65536. For the probability of x less than or equal to 2, so that is the sum of the binomial of x where x is from 0 to 2. So that is the binomial of 0 plus the binomial of 1 plus the binomial of 2. Your calculator has the summation notation, so you can use that. And the value is approximately equal to 1. Sorry, I have a wrong calculation. Again, summation of 20 combination from 0 to 2. This is 2.012 to 0.0123 times 10 to the negative 4. For letter C, the probability of x is greater than or equal to 9 would be the summation of the binomial of x from 9 to 20. So that is from 9 to 20. This is 0.7483. For letter D, 3 to 5. So that is the summation of the binomial of x from 3 to 4. 5 is not included. So that's from 3 to 4. So that is 5.7077 times 10 to the negative 3. Next. The phone lines to an airline reservation systems are occupied 40% of the time. So we have the probability is 0.4. Assume that the events of the lines are occupied on successive calls are independent. Assume that 10 calls are placed to the airline, so n is 10. What is the probability that for exactly 3 calls the lines are occupied? So x is 3. So this would be 10 combination 3, 0.4 raised to 3. And then 1 minus 0.4 raised to 7. So 10 minus 3 is 7. So that would be 10 combination 3 times 0.4 raised to 3 times 0.7, 0.6 rather, raised to 7. So 0.215. What is the probability that for at least one call, the lines are not occupied? So for this one, x is greater than or equal to 1. At least one call. But the probability is 0.6. Not occupied. So it's the reverse of 0.4. So this is the summation of 10 combination x, 0.6 raised to x, 0.4 raised to 10 minus x, for x is equal to 1 to 10. .999. So 0.9999. What is the expected number of calls where the lines are all occupied? So the mean is the expectation. So that's NP. There are 10 trials. The probability that it is occupied is 0.4. So from 10 trials, we expect 4 times that the line is occupied. These are the references used for this video.